Yeah, so tonight we're going to just kind of talk about galaxies in general. We're going to talk about the different types of galaxies, some of the existing hypotheses on how galaxies are formed. Um, there was in December of 2020 database, an early database 3 release of the Gaia data. Pretty spectacular release in December of 20. And so the last time I gave this talk, I was on data release 2, and it was just been a dramatic difference in the amount of data and some of the graphics. Pretty spectacular. Um, so boy, I tell you, this has got to be my most favorite image of a galaxy. This is a picture I took personally up at Mount Lemmon 2 years ago on their zero 0.8 meter Schulman Research Telescope. This is the same telescope that Adam Bloch uses. So boy, I just figured that some of the aura coming off of the telescope I could absorb. It didn't happen, but that's another story. But it's a magnificent telescope, and this is the entire field of view. The field of view of that telescope is only 24 minutes by 24 minutes, and so M101 just perfectly fills the the entire 16 megapixel frame. So you typically hear about spiral galaxies and elliptical galaxies, and but we really have about 6 official classifications. Some are subcategories, of course. So we have the barred spiral, which is what our Milky Way galaxy resembles. Of course, we have galaxies that don't particularly have any shape, so we give them the affectionate name of irregular. And of course, we have regular spiral galaxies.
That's why.
And then again, we have galaxies which are typically, galaxies that are in the process of merging. And during that merger, they take on a very peculiar shape. And so we kind of put a category together for that. And then finally, there's kind of a cross between spiral and elliptical, and that's the lenticular, type galaxies. They have the same diffuse pattern as an elliptical, some spiral arm structure, and and a central core. It's as if it's a spiral, an aged spiral becoming an elliptical. So the first thing we're going to talk about is how the first galaxies were formed. Boy, there's a lot of controversy here. Of course, everything I'm going to talk about are hypotheses at this point. Just based on observational information that we have from the present day. And so that's essentially what we try to do, is build models based on present day observations, and then see if we can kind of work backwards and kind of home in on what might have been happening way back then when the first galaxies were formed. One thing we do know is, and I like this term, clumpy. I'll use that a lot tonight. That the early universe, right at about the cosmic microwave background, about 380,000 years after the Big Bang, was fairly clumpy. These are very, 1 in 100,000 changes in the background's temperature, but still in all, they basically are, clumpy in nature. There's essentially concentrations of baryonic matter that we're looking at here. We can't see the dark matter, We also postulate that the dark matter was also present at this point and was also clumpy. And we base that clumpiness story on dark matter on some of the really elegant dark matter maps that we have currently generated. And we're kind of back extrapolating that since we see clumpy dark matter now, that it was clumpy, back near the Big Bang. We also know that what really distinguishes a galaxy is in fact that it is bathed in a dark matter halo. And this halo actually makes up, when we weigh the galaxy and then look at the motion of the stars and model that motion, we come up with a ratio of about 80% dark matter and only about 20% baryonic matter. That's matter made up of quarks and gluons and that kind of stuff. So the scale is really heavily tilted towards dark matter, and virtually every galaxy that we've studied has, in fact, a dark matter halo, around it. This is an updated image of M87, black hole, from the Event Horizon Telescope. Superimposed on the original image, now we have this fantastic overlay of the magnetic field associated with the accretion disk. As charged particles move around the accretion disk around the black hole, they actually create a magnetic field. And so we were actually able to look at and measure and come up with a graphic here that essentially represents the magnetic field lines associated with the accretion disk. Pretty cool image. Now we find that most large galaxies that we've studied do in fact have supermassive black holes. However, not all of them. And so whatever model or whatever hypothesis we come up with, we're going to have to kind of come up with a multi-prong approach where some galaxies form with black holes and others do not. Most dwarf galaxies do not have massive black holes at their center. And in fact, one of our favorite galaxies to image, M33, strange enough, does not have a massive black hole, even though it is a fairly large galaxy. The Milky Way, as you know, has about a 4 million solar masses black hole, a supermassive black hole, which is actually fairly small in comparison to some of the other whoppers, like Andromeda is over 100 solar masses. And then, of course, there's M87 that has a whopping 2 or 20 billion solar mass, black hole. So what else do we know? Well, not too long ago, Hubble recorded GN-Z11, the oldest known galaxy. And based on its redshift of about 11.1, it's estimated to be about 13.4 billion years old, only about 400 million years after the Big Bang. Just for a matter of reference here, that Z number, which we use to indicate the redshift, for example, of M87. Let's see, where are my notes on that? Which is only 54 million light years away, has a Z value of 0.004. So this image from Hubble's ultra deep field at a redshift of 11.1 tells us that these were very hot young blue stars when this galaxy was formed, but now they appear completely redshifted to this irregular red blob that we see in the image. So we kind of have put a framework around. We have other models that suggest that potentially the first stars were formed about 150 million years after the Big Bang. So we've got a window for galaxies of probably between 150 million and 400 million years after the Big Bang. Those first galaxies started to appear. Now, what's going to be exciting, I'm keeping my fingers crossed, is that the James Webb Telescope is going to obviously be able to look farther back in time than Hubble. Hubble can look into the near infrared, but Hubble can go James Webb can go way past Hubble. And boy, there's lots of expectations of us actually being able to maybe even see population 3 stars. Now, population 3 stars are in fact stars that do not have any metallicity. They're just purely made up of hydrogen and a little bit of helium. Okay, so what we're trying to do is kind of pull all this observational stuff together and kind of come up with a couple of hypotheses about how these irregular, very young galaxies are formed. And then, basically that same hypothesis doesn't really lend itself to figuring out how an actual disk galaxy is formed. Now, there's some really nice work being done out at Ohio State University by Adam Leroy and his group. And he's put together, what seems to make sense. He calls it, the star clusters hypothesis. And basically it starts with that same premise that we saw with the cosmic microwave background, that the distribution of matter in the early universe was in clumps that consisted mostly of dark matter. Now, these dark matter clumps pulled in hydrogen gas clouds. And then these gas cloud clumps collapsed into actual star clusters. And so the building blocks for these irregular first galaxies are in fact star clusters that are still bathed in dark matter. These clusters of stars and their associated dark matter merged to form even larger clusters. And then finally, a series of these larger clusters clustered together to form that first irregular shaped galaxy. Okay. And again, this is a hypothesis, based on observational information from present day. Now, there's all kinds of stories out there, and there's a couple summaries on Wikipedia. There are a lot of hypotheses flying around about how disks type galaxies are formed, and it, pretty much is a variation of the theme of the irregular galaxy with a twist. Again, we start off with that early universe being very clumpy. And consisting again of all of these pockets of localized dark matter. The disk galaxies probably formed again through the collapse of individual smaller gas cloud clumps, kind of like the star cluster story, only with a slight twist to it. And the twist is that this dark matter framework with these smaller gas cloud clumps interact gravitationally, putting tidal torque on each other and act to give them some angular momentum. Now, basically I am not a mechanical guy and don't understand tidal torques that well. But so this is a proposed mechanism or hypothesis about how these disks actually start forming and start rotating and then flatten out, just like you toss a pizza and spin a pizza. The faster it spins, the flatter it gets. And then observationally, that's what we see. We see these disk galaxies, very flat on, when we see galaxies on edge. So at this point we have a spinning non-homogeneous cloud of disks for a non-homogeneous cloud disk forms, and then this each of the smaller clouds within this disk gravitationally collapse, forming stars. Now the idea here is that this is kind of a one-stop shop here, where the stars and the disk galaxy are kind of forming together. And so again, this is just extrapolating from empirical data. So those are the two current hypotheses, popular hypotheses on one explains that 13.4 billion year old galaxy that Hubble saw, and then the second hypothesis explains all of the disk galaxies that we see in the cosmos. Now this was a diagram put out by Hubble. A lot of people think that this diagram moves from left to right, and it doesn't. So Hubble came up with these classifications of so if you want to look at any kind of evolution, and we see examples of this again observationally, and we're even proposing that when the Milky Way, which is a nice spiral galaxy, merges with Andromeda in about 3.5 billion years, both galaxies are going to lose their spiral shape and form an elliptical galaxy. And so really this diagram kind of moves from right to left, with different, below with different bar type galaxy structures, SBC through SBA. And then the non-barred spirals running from SC to SA. And then there's this lenticular beast there at SO, which is a spiral galaxy evolving into a elliptical. And then we got various stages of ellipticals from E7 all the way down to EO. Okay, probably most of you are familiar with this diagram. And so again, from observational, I mean, we see examples all the time. NGC 5331 and 31-1 and 2. We see these two galaxies just on the verge of starting to merge. Still classified as two spiral galaxies at this point. Then we have the Atene galaxy, basically, which is two galaxies that are well into the merger process. This merger is actually, only occurring about 45 million light years away from us. We basically estimate that this merger started about 1.2 billion years ago. So this is well into the merger. And of course, when two galaxies like this, merge, especially with the merger of the gas components of the cloud and gas components of the galaxies, these galaxies enter into what we call a starburst phase. All that pink and reddish areas are star formation areas. And then, for lack of a better name, we can't call this spirals anymore, or we can't call this an elliptical, and so we call this a peculiar shaped galaxy. So, you know, what I always find amazing when I give this part of the talk and talk about, you know how galaxies are really the building block, of course, of our entire universe. When you go through the various building blocks and how they continue to grow, it just becomes a phenomenal story of distances and unimaginable dimensions. I mean, I'm okay, and you know, we have an easy time thinking about the little local group of galaxies that we're in right now. In fact, we affectionately call it the local group. There's about 54 galaxies in our local group. Two largest ones, of course, are the Milky Way and the Andromeda, Galaxy. There's the large and small Magellanic Clouds galaxies, and then the Sagittarius dwarf, which we have now, with some new Gaia data, basically is in the process of actually merging with the Milky Way. In fact, some of the Gaia data suggests, one paper I looked at yesterday suggested that actually the Sagittarius dwarf galaxy has actually passed through the Milky Way 3 times already, and each time leaving a trail of stars. And what's telltale about that is that there are these stars that Gaia has found that are moving in the opposite direction of the majority of the stars that are rotating around the Milky Way's central core. And so that's very suggestive that the Milky Way has cannibalized and has eaten smaller galaxies, and how those stars were introduced into our galaxy. Basically, in this particular case, we have found stars moving in the opposite direction of the majority of the stars. Pretty cool. Then again, I don't have any trouble dealing with clusters. We talk about clusters all the time. In fact, we use clusters to sometimes map out dark matter distribution, and we've seen examples of the bullet cluster as two clusters move through each other, and the gases basically move through and start and form these really hot barriers as the two clusters pass through each other. And so a cluster is defined as anywhere from 100 to thousands of galaxies that are all essentially bound by gravity, of course. We are actually on the edge of the Virgo cluster, which is someplace between 1,300 and 2,000 galaxies. Well, and then we take it up a level, and we talk about superclusters. And so everything obviously here is building on itself. So where we had a group, which, lots of groups made a cluster. Now we've got lots of clusters that make superclusters. Basically, now we're talking about hundreds to thousands of clusters together. And we are actually in the Virgo supercluster. And then, boy, we have to take it up another notch, and this is where it just becomes phenomenal. We start talking about giant superclusters like Lenticular, which is hundreds of 100,000 superclusters stretching out over 500 million light years across. And you can see our little Milky Way on one of the outskirts of this giant supercluster. And then, of course, we've got adjacent super clusters or giant superclusters. And our neighbor is Perseus Pisces, and again a similar looking chains of superclusters making these giant superclusters. Boy, and if this isn't enough, we have to take one more step back and look at even a higher architectural structure or hierarchy, and we start looking at filaments. And filaments are in fact strings of these super and giant superclusters, actually forming what we call the cosmic web. And these filaments are literally millions to billions of light years long. Okay. Oh, by the way, if you've got any questions, just unmute your. Thomas, can somebody unmute themselves? Can somebody try and unmute themselves?
Yes.
Yeah, you can.
Yeah, you can.
Yeah. Okay. Good. Okay. So as I'm cruising along here, if there's any questions, don't hesitate to interrupt me. We should have a few minutes afterwards. These university lectures are designed to be about 45, 50 minutes long with 10 minutes of questions. One of the fantastic surveys, sky surveys that shows this cosmic web structure is the Sloan Digital Sky Survey. Pretty cool. And in fact, there's an entire building that literally rolls off. When I was thinking about observatory designs, this was one of the things that I was thinking about. And we have talked about how a shed or a building rolls off. Well, that's exactly how the Sloan Digital Sky Survey telescope works. There's literally an entire building around this, and the whole building rolls off on rails, exposing the telescope. This is a 2.5 meter f5 modified RC telescope, Alta Azimuth. And it's actually located in New Mexico, in the southeastern portion of New Mexico at Apache Point. And it uses as its detector 30 2K by 2K CCD chips, giving a total of about 120 megapixels. This survey has been going on for gosh, I forget how many, 10 years now, someplace in that ballpark. And right now it's the most detailed 3D map because in addition to the CCD camera, they can actually put in little a plate with all these holes in it with fiber optic tubes going to spectrographs. So they can actually look at the spectra of these galaxies as well as mapping the galaxies. And they have, they have, let's see, over 1 million spectra now. And they go out to about 7 billion light years in galaxies. And so this currently is what the current map looks like, and boy, I mean, there's that cosmic web. Here's that redshift Z number again. Now this is only looking out to a Z number of 0.14. So that's what was that? That was about 7 billion light years. Okay. But now, if you look at some of the computer models that we have generated, there's an amazing, as we look at the nearby galaxies and we start looking, farther back in time, we actually see this cosmic web taking on, a remarkable agreement between the model here and what the digital sky survey Sloan telescope has done. Now, taking that Z number even further, there's an amazing correlation between the extremely high Z scores and on these cosmic web models and agreement with the cosmic microwave background. Okay. Right now, there's a lot of correlation, but there isn't been anybody strictly making any solid correlations or causations at this point. But it is an incredible correlation between what the cosmic microwave background looks like and the cosmic web. All right, so in the last 10 or 15 minutes, I'd like to talk about our, kind of focus in a little bit on our own Milky Way, which I saw for the first time 2 years ago when I actually went up to Mount Lemmon up at 9,500 feet. It was a new moon. I had booked that telescope on a new moon night. And boy, it was so dark up there, you could not see the hand in front of your face. And for the first time, I actually got a good view of the Milky Way, and it was just totally amazing. So these spectacular images that we see are really, mainly due to very good dark sky seeing conditions. Just to impress your friends, you can point out, where the galactic center is of our Milky Way, just by finding the spout on Sagittarius, and basically looking at that space between the spout and the tail of Scorpius, and that's the approximate galactic center of the Milky Way. We basically, and of course Gaia is really helping us, get a firmer view of what our own galaxy looks like. But we certainly have postulated that the Milky Way is in fact a barred spiral, and that the actual closest twin to the Milky Way is NGC 6744. You're probably all pretty much familiar with the various components of the Milky Way, but we do have the central bulge and a bar formation in the center of our galaxy, along with that 4 million solar mass supermassive black hole. We have these spiral arms, basically, that contain a lot of the molecular clouds and the star forming regions. Here we are out in the suburbs, about 26,000 light years, from the central core. These are the spiral arms of and of course they all have names. At some point, I think we ran out of names other than their girlfriends. Outer arm, Norma, so. But one of the interesting things about when people look at this image of our spiral arms, you are all aware of the fact, right? I'm not telling you anything new, is that the spiral arms are not rotating, right? In fact, over the millions of years, it takes 225 million years for our solar system, our star, to make one trip around the nucleus. But the arms are not moving. The stars are actually moving through the arms, and what we're actually seeing is like, as you're driving down the highway, you know, somebody puts on the brakes and there's an accumulation of cars and gas and stars. But then that gas moves through, and so do the stars. So the arms are basically congestion points of gas and stars, and they are not themselves moving. The arms are stationary, and everything else is literally moving through the arms. Okay. How many thought? Because if the arms were moving, they just keep winding up tighter and tighter, right? But this structure, you know, maintains its structure for the last 10 to 12 billion years.
The whole problem with winding is actually already a big problem in astronomy anyways. If you guys want to look it up, it's called the winding problem. It deals with the rotation of spiral galaxies.
Yeah. Yeah. Cool. All right. So let's just, just some dinner conversation here. I mean, we, the range of galaxies, one of the smallest galaxies, a dwarf galaxy is only about 225, 222 light years across, all the way up to our Whopper friend IC 1101, which is 6 million light years across, and of course it's a giant, elliptical galaxy. There's our M87, which has made all that news, and what we've imaged its central black hole. It's 1 million light years across. So we're and Andromeda is about twice the size of the Milky Way. So here we are. I mean, even though it looks like we're on the smaller size, we are still in about the top 10% of galaxy sizes. We know how much the Milky Way weighs. We can easily weigh the Milky Way, and the way we do that is look at the motion of the globular clusters that are above and below the plane of Milky Way, and we can actually look at their motion and literally weigh our galaxy. So we know how much mass there is, within the galaxy. And so, but we get this pretty widespread number of stars, between 100 and 400 billion stars. And that range comes into what you just assume as the average star in our Milky Way. And with Gaia and TESS and all these other now space probes, that is continuously changing as we get better and better surveys. And now, of course, we know that the majority of the stars are actually on the light side. That there are the majority of the stars in our Milky Way are actually red dwarfs. Okay, and so that number of stars keeps actually inching up, and now we typically talk about 300 to 400 billion stars. Based on dividing the mass of the entire galaxy by what we think a typical average mass is of the stars. Okay, I think we already talked about this, but what's interesting is so our supermassive black hole is about 4 million times more massive than the sun, and it's estimated to be about 27 million miles in diameter, and of course our sun is about 26,000 light years from the center. I mentioned this earlier. It takes our sun 225 million years to make one trip around the Milky Way core. And since the birth of our sun and our solar system, we have only made about 20 trips around the galaxy. Okay, And so I don't know. I just find this particular fact pretty amazing. So I've got some really cool data here. That's fairly. When I did this talk last 2 semesters ago, or there was the third data release from Gaia hadn't come out yet, and so the information I'm presenting tonight is hot off the press. There was a third release of Gaia data, basically now bringing us to up to 1.8 billion stellar distances have been mapped. But in addition to the distances, there's what Gaia's claim to fame is of course it's also looking at velocities or motion, vectored motion, and the accuracy of Gaia is just amazing. It can position. It's about 1,000 times more, has about 1,000 times more resolution than Hubble, and it can actually position a star to within a hundredths of an arc second. Now, the other thing, of course, which opens up just amazing amount of additional data and information, is Gaia measures very accurately the brightness and the spectrum of these stars. Gaia was actually launched, went into operation back in 2013. And so over the last 8 years, we've basically have data now on 1.8 billion stars. And I'm going to show an animation, or actually a little movie of all of these stars in motion. Our previous survey, let's see, Hipparcos satellite, basically. Our previous maps were only 120,000 stellar distances. Okay, this is hot off the press. This is the early release data from, now, this is not a photograph. This is a map of the stars that have been mapped by Gaia. And so it's an incredible, map of actual star locations. This is zooming in on the galactic center, but the images here are just really striking. Now, one of the because we know the distance, we know the spectrum, and we know the brightness, we can calculate luminosity and the temperature of these stars, and we can actually now make an extremely accurate HR diagram. And this is one of the newest diagrams from Gaia, and it's just incredible detail, showing the main sequence, showing the white dwarfs and the 2 giant branches, the red supergiants and the blue supergiants on the left. Just an incredible looking HR diagram, based on what we've seen previously, in comparison to what we've seen previously. Now, the one thing that is just amazing is Gaia can actually show us maps of the velocities of groups of stars, and what we see in these maps is whole populations of stars are moving in groups or groups of clusters of stars that are moving at similar velocities. Just an amazing, set of maps now. Now, this next one just blows my mind. We can now measure the rotation, the rotation of the Milky Way. We can actually see the stars that are coming towards us in the blue, and the stars that are moving away from us. So Gaia has now generated this map that is actually tells us what the rotational velocity is of the Milky Way. I mean, just how cool is that? So let me just show you. This is only about a minute long, and I'm going to just pause it here in a second. Okay, just so you, because this goes by pretty quick. So we're gonna look at the recorded motions of 40,000 stars out of this data release 3. And then basically what it's going to do is the motions are shown as little short arcs on the sky, spanning 80,000 years each. And so what we're going to do is we're going to actually, so we can run the Gaia data forward and backwards. And in this particular in this particular mapping, I hate to even call it an animation because animation implies that it's not real. This is real data. And so what we're going to do is see how the stars have moved, and will have moved in 1.6 million years into the future. All right, so let me unpause this. There should be music with this. And every once in a while you'll see something like that go through. That's an asteroid. Because the other thing that Gaia has done, and it was hard to see. Whoops, let me just back this up a little bit. And pause it here. You can actually see, and things get a bit cluttered here, but this is the Large Magellanic Cloud here, and the small one is just a little bit over here, but it has actually mapped the motion of the Magellanic Clouds as to the dwarf galaxies as well, and they're actually moving towards each other, which is really pretty cool. And there's actually a trail or a gap as you really crank up the brightness, in looking at the Magellanic Clouds, that you can actually see a bridge forming, between the two galaxies. There is so much I could give I could spend a whole hour just on all of the Gaia data and the findings and the graphs. Actually, I wasn't even going to bring up the Magellanic Cloud, but I thought it was pretty cool that it was actually visible, within this diagram. All right, so let me do this, and then hopefully I can get back to my presentation. Okay. So we're just gonna end on a happy note, of course. As you all know, we're on a collision course with the Andromeda Galaxy, and so in about 3.5 billion years, the night sky is going to look pretty spectacular. Andromeda right now is about 2.5 million light years, away, and is about twice the size of the Milky Way, but it's approaching us at about 245,000 miles an hour. And unfortunately, somebody who really jumped the gun has already named the elliptical galaxy that's going to form, and it is just a dumb name. It's called Milkdromeda. No imagination there, at all. And so we postulate that these two beautiful spiral galaxies will actually become one elliptical giant galaxy. So here's what M31 looks like right now, thanks to Gabe's work. And if your eyes were in fact sensitive enough to do a little, to do some integration, you would actually see that in the night sky presently, and this is going to change in a couple billion years, but the Andromeda Galaxy is actually 6 times, apparent size is 6 times larger than the moon. So the moon is about a half a degree across, and Andromeda is about 3 degrees across. So you can fit 6 moons, across Andromeda. And so 3.5 billion years from the night sky is going to look really spectacular. Andromeda is going to fill the night sky, and it's going to start merging with the Milky Way. Now, chances are, and again, the distances are just so unreal. The distance between stars, even though these 2 galaxies are going to merge, it is extremely unlikely or improbable that any 2 stars will actually ever collide. Now, are there going to be tremendous gravitational effects between the 2? Absolutely. The Earth won't be around anyway, in 4 billion years, but we'll be someplace inside of our sun, I would think, at that point. But so just like we saw in those images of that irregular galaxy, so at about another 500 million years, there's the two galaxies are going to do this gravitational dance in the sky. And so, but wait a minute. Okay, we all know that the universe is expanding, and in fact, the universe is not only expanding; the expansion is accelerating. So, why in the world are Andromeda and the Milky Way going to collide with each other? William?
You want me to answer that question?
Yeah, come on, you can answer that question.
Oh, okay. Well, I would assume that they're both within like the gravitational bounds of one another, but I don't really have the domain to answer that because I'm not completely sure.
Yeah, but I know you well enough where yeah, if you think about the local group that we're in, all of the 54 galaxies that are in our local group are gravitationally bound to each other. And so when you basically have local effects, the local gravity is going to overpower the expansion of the universe effect, right? So it is local gravity is still going to win out over the expansion rate of the space between the galaxies. Okay,
makes sense.
It's kind of like running up a down escalator. The down escalator is carrying the galaxies apart, but if you have enough energy or gravitational force to run up that escalator, you can actually get to the top and collide with another galaxy.
That makes me question something myself. Could that possibly mean that all of the local group galaxies will eventually collide into one another?
That's a real good given as you saw in the local group where we already know Sagittarius dwarf has collided with us probably 3 times already, and the large and small Magellanic clouds are pretty close. Remember, galaxies, especially big spiral galaxies, get to be bigger by actually cannibalizing smaller galaxies. Now they have to be less than about 40%. So the spiral has to dominate in order to maintain the fact that it's still a spiral. But when you start getting the galaxies that are of a comparable mass and size, then that spiral is completely disrupted.
Yeah.
But good
and
question.
also,
yeah.
And also, elliptical galaxies normally arise from galactic collisions, anyways. Specifically, the larger ones, not the smaller ones, because the smaller ones are just basically large globular clusters.
Right.
So yeah.
Okay, so I thought I would end again with another fantastic image from one of our club members. Arun took this image of the Milky Way up on Kitt Peak down in down in Tucson. So all right, so we're at the end of the hour. Any other questions, comments, or anything anybody would like to add?
I would like to say one thing about the peculiar galaxies. There's another type of peculiar galaxy that I'd like to add. It's called the active galactic nuclei, or active galactic nucleus. Many galaxies are technically peculiar galaxies because they have active galactic nuclei. It basically just means that they have extremely luminous, like an extremely luminous central core. So like even lenticular galaxies themselves, they have really bright cores, so they technically could be considered that.
Yeah, well, okay, so you're kind of getting into a whole different kind of classifications, active galaxies, and I assume you're talking about quasars.
Well, not only quasars, but like lenticular galaxies or even M87 itself.
Mhm,
That's technically because a lot of them go by multiple classifications. So
mhm.
that one's also technically active galactic nuclei. The only time when it's ever really considered a like true single classification would be when it's on the Hubble sequence, I
Hmm.
think.
Yeah, okay, so I guess I'm a little confused between because galaxies go in and out of having an active nucleus.
Hmm.
And so when there's supermassive black holes are feeding and there's a lot of accretion disk activity and just a lot of material going into the black hole, their nucleus is very active, but that can shut off. And so I've never really heard of whether the nucleus is active or not, changing its configurational shape,
Hmm.
if you know what I mean.
Yeah, I know what you mean.
Yeah.
I mean, I think the fact that it is technically unstable, though, that the core would be unstable in that situation would kind of classify it as an active galactic nuclei. And a lot of it's based off what it is emitting. So what the core is emitting, like how bright it is in a particular wavelength. Like a
Mhm.
radio galaxy, for example, is bright, releases a significant amount of radio waves. Or like if you think of, I think it's like Cygnus X1, I think it is. They release a lot of X-rays.
Mhm.
That's essentially what an active galactic nuclei is. I'm not really completely sure why they do that, but that's all I
Mhm.
can really say.
Okay. Uh, well, you'll have to sign up for my class. I actually give a whole lecture on active galaxies and quasars and all of the different classifications. And one of the things that we have found is it turns out whether it's a radio galaxy, a radio, or a quasar, or we take it on one step not higher, a blazar, is all a function of the orientation of the core of the galaxy relative to the observer. And so what can look like a radio or an X-ray emitting a galaxy is because we're not looking straight down the barrel of the galaxy.
Are you
So you can,
saying, are you talking about red shifting? I'm not really sure what you mean by that specifically.
yeah. Well, okay, we can actually measure the different components by looking at the Doppler pieces, but we can also look at the energy output of a galaxy,
Hmm.
and depending on its orientation, we can actually see. And I've got a nice slide that shows the various orientations that basically then account for the different classifications of the active nucleus. So you
Interesting.
can actually be looking right down the barrel, and we would classify this and look at the highest energy output of that blazar or quasar. but tilt that central beam away from us a little bit, and then we're going to see more X-rays, and we're going to see what we would then call a radio telescope, a radio galaxy.
Wow, I had not known that. That's very interesting.
Yeah. Yeah. Any other Kevin? You're going to hear this story in about 3 weeks.
Dennis, I have a question.
Yeah.
What is known about the spiral arm formation?
About the what? Sorry, I'm sorry.
Spiral arm formation.
You mean about
how the spiral arms are forming, or why they formed?
Oh, sure. Well, that's what I had mentioned is really what happens is as the stars and the gas are rotating around the galactic core, there is literally slowing and just like on a highway where cars bunch up and then speed up and slow down. For example, our sun has actually moved through various spiral arms. We won't always be, I forget what the name of what the arm is that we're in right now. We're not going to always be in that arm. We're going to actually eventually move out of that arm, out of that congestion, be in some open driving space, and then we're going to be in yet another arm. So these arm structures that you see in a spiral galaxy are really congestion points of gas and stars that are basically that you will in fact pass through eventually, and so in our 20 trips, we have been in every one of those arms.
So Dennis, is that a gravitational effect that's happening, that's causing things to bunch up?
More than likely. I mean, it's I mean, we, and there whether there's any dark matter component to that or not, we don't know. But remember, 80% of the mass and what controls actually the majority of the movement of the stars in our galaxy is dark matter, not the baryonic matter.
So Tomas, that is a really, really good question. All I can say is that we technically, scientists haven't completely answered that yet. They believe that the spiral arms are due to pressure waves, and it kind of sums up what Dennis was saying about like basically areas of congestion. Obviously, there's more mass in a region with more congestion, and I mean it gets all into like gravitational waves and all that crazy stuff. But they basically call it like the pressure wave theory. Mm-hmm. So basically, like gravitational waves like create this spiral shape, create the spiral arms. But again, we really don't know that yet.
I don't think these are general relativistic gravitational waves, though.
No,
I think they're density waves.
They're baryonic.
They're density. Yeah. That's
But I think the thing that people find amazing is that the arms aren't moving, but the gas and the stars are.
But what makes them visible then, if the material is moving? So why we see a bright lines as arms if the material is moving between them?
Yeah, but it's differential, right? I mean, and so and again, the best analogy I've heard lecturers give is you're driving along 94 at 75 miles an hour, and somebody in front of you puts on their brakes, and you start to slow down, so does the cars behind you, and all of a sudden you've got this wave of slow moving traffic, and that's your arm, because along with that are the gravitationally attracted gases as well, and then you move past that congestion, and now your velocity is increasing again. At least as how I've seen people try to explain it. I don't know, Gabe, have you seen a better explanation?
No, I think that's a good analogy. I myself am not, I don't know too much about exactly what's causing it aside from that type of behavior.
Mm-hmm.
But within a, say you're given a starting condition of you have spiral waves, just like we have in our galaxy, and then you set it in motion. The next question is, how does that propagate forward in time? If you're a star inside that spiral wave, how do you move out of that wave and into the next wave?
Right.
I would presume that as you're rotating around the galaxy, you're moving out of that wave that's a higher density behind you, so you're moving out of it slowly.
Mm-hmm.
And then once you start encountering the next wave, you're going to move towards that wave faster. So
Right.
I'm sure that as you're going around the galaxy, you're not in a perfectly circular orbit around the galaxy. You probably have some velocity and increase and decrease and things like that. And so that decrease, as the stars come into the wave, they are accelerated into it, and that causes that sort of clumping. And then as stars move out of it, they are decelerated, and that also contributes to that clumping. But the net flux through that wave is still the same. You have the same number of stars going in, or I shouldn't say stars, I should say mass. You have the same amount of mass going into the wave as going out of the wave. So there's never really a total accumulation of stars in that spiral arm. But that feature will stay there, but the stars themselves continue to propagate around the galaxy relatively unimpeded, aside from that variation as they're going in and out of that spiral arm.
Yeah, that makes sense. Thank you.
That's great.
Mm-hmm. Well, good. Well, thank you very much.
Thank you, Dennis.